So what we have here is a ball, and you imagine if I take this ball and bounce it off the table, it'll bounce off that table, and if I do that exactly the same way each time, then what will happen is that it'll hit the same point on the wall. Imagine if we had 1,000,000 balls, we could control it so that each and every one of them hit the table in exactly the same way, exactly the same velocity, they'd bounce off, and we'd end up with a very well-defined dent in the wall.
Okay.
If we then, for example, just scatter those balls, take them and fire them off at different angles, then what you'll find is that the wall will cover up with different dents in the wall, and we'll end up with a sort of random distribution of dents in the wall.
Electron is a negatively charged particle, and it is enormously important. Mendeleev didn't believe in electrons. He thought atoms were solid and you couldn't break them and weren't made up of anything else. And he believed this till he died in 1907. But electrons are enormously important for chemists.
So now, if we imagine that instead of we're in the real world, we shrink everything down so this ball becomes an electron, or we can think of this as being an electron, what we actually find, remarkably, is that we get these bands. We get this very well-defined pattern of here where there are lots of dents, here where there are practically none, here where there are lots of dents again. And those bands have a well-defined spacing, a well-defined separation. Why do electrons behave so differently from little balls? And maybe that's because, well, actually they're not little balls. There's something different from little balls. What could that be? Well, let's go down to the lab and we'll see another experiment whereby we see these patterns, and maybe the patterns we see in that experiment will help us to understand really what these electrons are. Right.
When I teach the students in their first week of coming to university, I tell them about electrons, how they behave in atoms. And they find this is very hard because electrons, if you treat them one way, behave just like a particle. An electron is something, a negative charge, that can be transferred between one atom and another, rather like changing money. But on the other hand, if you want to understand the structure of the atom, then you have to treat the electron as a wave.
Hello, George. What we have here is not an experiment with electrons, though we'll get to that. What we have here is an experiment with light. In this case, we've got a laser. The important reason we're using a laser and not, for example, a light bulb is that in the laser, the photons of light all come out in step. So we've got an obstacle through which those photons, those little packets of light, have got to pass. And so if you follow this through, you follow the path of light, down here we have the light, and instead of it all piling up, what we see is this pattern exactly like that I was discussing in terms of the electrons. And this is something called the double slit experiment. We have two slits here. The key thing here is that what we have is light. Light is a wave. That wave is coming through and it's interfering constructively, destructively, to form this type of pattern. The key thing here is related to how those waves interfere with each other. But we see exactly the same pattern in terms of this, these bright spots, these dark spots, when we do this experiment with electrons. And that leads us to think, well, hang on, if we're seeing exactly the same patterns with photons, which are a wave, and we know that, as electrons, then it leads us to think, well, maybe the electrons are actually not just little hard balls, little billiard balls, they actually have a wave-like nature.
And the problem is that you have to explain the thing mathematically. And as soon as you go into the maths, the difficulty is that unless people are very good mathematicians, and I'm not, it's not very clear what the equations mean.
Everyday common sense does not allow us to describe it in simple words. The concepts are too elusive and slippery for the English language, but it has these particle-like qualities which it always takes with it, such as its mass, its momentum, its spin, its lepton number, and so on. And that always remains. So if a particle comes along and hits something, that is always conserved, and this quantity remains the same. But when it hits things, it does so as a wave, scattering off things as though it were a wave. So all the time it has these two elusive characters going on. And I don't know, physics when you're 18 is based on common sense, but when you've gone through all this, somehow you get used to it. You don't actually like it, you just get used to it and learn to live with it. And that's the language that seems to fit.
So back in the office, what we were doing was this, considering that if those electrons were billiard ball-like particles, that when we fire them at something, they'll all pile up in one place or they'll spread out randomly. What we have here is the actual experiment where we're taking a sample and we're firing electrons of that. Those electrons are bouncing back from that sample and we're looking at the pattern they form. Now, if they were little billiard balls, then we wouldn't expect to see, what we'd expect to see would be a random sort of splurge of electrons. That's not what we see. What we see are very, very well-defined peaks, and those peaks and spots arise from the wave-like properties of the electron. And what we have here is, instead of having a slit like we had with the experiment with the photons of light, what we're using, because the wavelength of the electrons is so much smaller, is we're actually using the atoms at a surface to diffract the electrons.
One of the things which I think perhaps students find particularly difficult is that when you're treating the electron as a wave, you can't really talk about it being there or there or there, because a wave is everywhere in the volume that you're considering. And therefore, the idea that everything is very delocalized is difficult for people to understand.
And back in 1923, it was a piece of kit that resembled this that actually gave us really the fundamental proof that electrons had wave-like characteristics. And so it was a couple of people called Davison and Germer managed to measure a pattern just like this that we've got in here, or very similar to this, and they realized, well, hang on, that's a diffraction pattern. That means that the electrons must be waves, or must have wave-like character.